Welcome to Proof in Propositional Calculus. This is Dr. Teo Kim Heng, Informatics Academy. Consider the following horn dragon case study. The premise are, if the dragon is mythical, then it is immortal. But if it is not mythical, then it is mortal and it is mammal. The dragon is horned if it's either immortal or mammal. The conclusion is the dragon is horned. The challenge is to prove that the argument is valid. In other words, we need to prove that the conclusion follows the premises logically. In other words, the conclusion must be true whenever the premises are true. The first step toward formal approach is formalize the challenge. In algebraic approach, we define a set of variables, and based on the variable, we define a set of equations. So here we adopt the similar formal approach. Define a set of atomic proposition, and based on the atomic proposition, we define a set of rules and facts. The first statement, if the dragon is mythical, then it is immortal, can be written as A implies B, where A represents the dragon is mythical, and B represents the dragon is immortal. For the second statement, if it is not mythical, then it is mortal and it is mammal. It is not mythical means not A. It is immortal means it is not immortal, so it can be represented as not B. It is a mammal, then we represented by a third atomic proposition. So the whole statement can be written as not A imply not B and C. The third statement, the dragon is horned if it's either immortal or mammal. The dragon is horned is a new concept, so we represent as atomic proposition D. So D follow the condition if it's either immortal or mammal. Either immortal or mammal means B or C. The whole statement can be formalized as B or C imply D. Now we are ready to translate the case study into pure logic argument. The premises are A imply B, not A imply not B and C, B or C imply D. The conclusion, the dragon is horned, can be simply written as D. So the whole challenge is to prove that this argument is valid. In other words, the conclusion will hold whenever the premises are true. One way to prove the argument is using truth table. So what we want is to prove that premise 1 and premise 2 and premise 3 imply conclusion is a tautology. We can use an online truth table tool such as the one provided in UT, Texas. First, we translate the argument into text format, and then we go to visit the online tool to verify that it is a tautology. The online tool will help us to create a truth table for our argument. we're supposed to fill in the truth table column by column. However, here I just fill in the last column, assuming all true. And here you see that the two show green color, meaning this column is all true. The advantage of using truth table is that they require no creativity. All we need to do is just create the truth table and verify that the last column is always true. However, the size of the truth table grows exponentially with the number of atomic proposition. When the number of atomic proposition is small, for example 4, in our haunted dragon case, you got 16th row in the truth table. However, if we got n atomic proposition, you will see that the truth table has 2 to the power n rows, which is too big for practical problem solving. For complex argument, using truth table is not practical because the table is simply too big. We are interested in deductive inference, in which we use rule of deduction to make conclusion from the premises. There are many inference rules. We discuss a few of them for the proof of the horned dragon case study. Here are some general inference rules. The first one is disjunctive syllogism. If we know that X or Y is true, but X is not true, then Y must be true. If we know that X is true, then we can actually write a less stronger statement X or Y. If we know that X and Y is true, then we can write a weaker statement X is true. Same thing here. If X and Y is true, Y must be true. During the proof, if we have proof that X is true and later on proof that Y is true, then we can write the conclusion X and Y is true. There is this principle of excluded middle, which states that X or not X must be always true without any premises. Here are some inference rules based on tautology. The first one is used to remove implication. So when you see P imply Q, you can always replace it by not P or Q. Distribution rule. Conjunction can distribute over parentheses for all, and all can distribute into parentheses for n. So P and Q or R can be distributed as a P and Q, P and R all together. P or Q and R can distribute, become P or Q, P or R, n together. De Morgan rule. The negation can distribute into parentheses, and the n change to all change to n. So overall, not P and Q can always replace as not P or not Q. Not P or Q can be replaced as not P and not Q. Double negation rule. Not or not P can always replace by P. The two negation operator will cancel. Here are some inference rules for the implication operator. Assuming we have two implication statements x1 imply y1, x2 imply y2. Then the left hand side can be combined using conjunction operator or disjunction operator. Right hand side can be combined using the corresponding operator too. Modus ponens. If we know x imply y and x is true, then we can conclude that y is true. This is one of the most famous inference rule. Syllogism. If we know x implies y, y implies z, then we can conclude that x implies z. In other words, transitivity holds for implication. Contrapositive. X implies y actually is identical in meaning as not y imply not x. These two are identical. Using the inference rule that we discussed so far, we can prove the dragon key study. We start by the three premises. Then we combine the first two statements so that the left hand side all together and right hand side all together. Now we apply distribution rule to the right hand side of fourth statement. So B or not B and C can be distributed as a B or not B, B or C, and together. Now we can apply syllogism for statement 4 and 5. Statement 4 is in the form of x imply y. Statement 5 is in the form of y imply z. So overall we can have x imply z. Next, we can use principle excluded middle. We say that A or not A is always true. From statement number 6 and 7, we can apply modus ponens. X imply y, and x is true, therefore y is true. From state number 8, x and y is true, we can conclude that y is true. Now, from statement 3, x imply y, and x is true, we can conclude that y is true. Therefore, D is true. And we have derived the conclusion. Deductive inference proof normally give a short proof. However, it is very difficult and tedious to find the proof. It is difficult because there are so many inference rules to choose from in each step. Instead of many rules of inference, ideally we want only one inference rule. Then we can use this rule again and again to find the proof. This is especially applicable to computer because computer can just apply this rule over and over again until it finds the conclusion. The rule of choice is called the resolution principle. Before we discuss resolution principle, we need some basic concept. A literal is an atomic statement or its negation. So P is a literal, not P is also a literal, assuming P is a atomic proposition. A clause is a pure disjunction of literal. So P or Q or R is a clause. P or not Q or not R is also a clause. But not P or Q is not a clause because it has parentheses. P and R is not a clause because it uses disjunction. A statement is in conjunctive normal form if it is a conjunction of clauses. So here's an example of a statement in conjunctive normal form. It is a conjunction of clause, two clauses. Given two clauses, the resolution rule make a valid deduction like this. Assume that we got B or A in clause form, not B or C in clause form, then we can conclude that A or C is true. We can imagine that B and not B cancel off, and the remaining literal will combine together into a resolvent clause. The reasoning behind resolution rule is as follows. If B is true, then not B must be false, therefore C must be true, and the resolvent is true. If B is false, then A must be true, and again the resolvent is true. In either way, A or C must be true, so the resolvent as a conclusion is always true when the two premises are true. The resolution principle is commonly work together with the refutation principle, also called reductio ad absurdum, RAA, which means reduction to absurdity. The principle says that to prove a statement P, we can assume the negation of P. That means not P is true. Then we try to derive a contradiction, which is asserted from the assumption that not P is true. If we derive such a contradiction, then not P must be false, and therefore the truth of P is proven. Now we are going to use resolution principle with RAA to prove legal document case study. The legal document has the following premises. First statement, it is legal if it is well-formed and it is valid. The second statement, it is valid if it complies with the schema. The third statement is a fact, it is well-formed. The fourth statement also is a fact, it complies with the schema. The conclusion is it is legal. As usual, the step 1 is to define the atomic proposition. So it is legal can be A, it is well-formed can be B, it is valid can be C, it complies with the schema can be D. And based on this proposition, we can define a set of rules and facts as a model of the premises. Define rule and facts from the premises. It is legal if it's well-formed and valid. So translate into B and C imply A. If it's valid, if it complies with the schema, translate into D implies C. If it's well formed, it's simply B. It complies with the schema, is simply D. The goal is to prove that it is valid. A, which purposely negated the goal following the principle of RAA or refutation principle. So after negate the goal, we have not A. And based on this rule, we would like to find contradiction. Because resolution principle work on clauses, so next step is classification of all the rule and facts. The first rule, B and C imply A, actually is already in the clause format, because if we remove the implication and apply De Morgan rule, you will get not B or not C or A. Same thing here. If we apply implication removal rule, we got not D or C for the second statement. B is already in a clause form, D already in clause form, not A already in clause form. Now we apply resolution principle to derive contradiction. We start from the negation of the goal, not A. So apply resolution principle, we try to get rid of not A. How to get rid of A, not A? We find a clause with positive A. So not A and positive A cancel, we got the resolvent not B or not C. Continuously, we want to get rid of not B, one at a time. After that, get rid of not C. So not B can be resolved with B, and the resolvent will be not C. Not C can resolve with C, and not D or C has a positive C. So after resolvent, we got not D. Not D and D give us an empty clause. So the negation of the goal, not A, leads us to a empty clause. An empty clause represents contradiction, and therefore the goal is proven by RAA or refutation. Empty clause represent contradiction can be seen here. To get the empty clause, you resolve not D and D. So, in other words, somehow before you get the empty clause, you got D and not D both true, but it is ridiculous. D and not D cannot be simultaneously true. Here is a brief guideline for classification. First, we remove the implication. A imply B always replaced by not A or B. Then we apply distribution rule, De Morgan rule, double negation rule until you find the statement in conjunctive normal form. Distribution rule distribute and or into parentheses. De Morgan rule distribute negation into parentheses. Double negation rule cancel to negation operator. Classification example 1. Assuming we have the following statement, not P imply not Q and R. First step, we can remove the implication operator. It becomes not left hand side or right hand side. Okay, now we have not P or not Q and R. This obviously can be replaced by P using double negation rule. Again, it's still not in conjunctive normal form. So we can apply distribution rule and then become P or not Q, P or R, N together. So we got one clause, two clause, N together. We have a statement in conjunctive normal form. Classification example 2. If we got statements such as this, we remove the implication. We got not P or Q or R and S. Not P or Q, we can apply De Morgan rule, become not P and not Q. So now we can apply distribution rule. Distribute not P into R and S, not Q into R and S. We end up, we have 4 clauses, N together. And we have a convert into conjunctive normal form. Let's look at another example of resolution with RAA. The premises are R1, not P imply not Q and R. R2, not P. The conclusion is R. This is a quite straightforward argument because the R1 can be weakened. You become not P imply R. And since not P is true, by Morris ponent, R will be true. But we want to apply formally the resolution principle with RAA. So we classify R1. Previously, R1 has been classified and divided into 2 clauses, P or not Q, P or R. And R2 is simply clause 3. The negation of the conclusion is simply clause 4. Now we can apply resolution principle. So clause 4 can resolve with clause 2. The resolvent is P. And P can resolve with clause 3 and result in empty clause, and the conclusion is proven following RAA. Note that we actually didn't use the first clause at all. This is the end of this supplementary lecture. Thank you for your participation.